We're live. Hello, everyone, including those watching on live stream. We have put this slide up here to say if you want to follow along with the kind of interactive live demo that we're going to be doing in this kind of middle third of this presentation, these are the prerequisites that you need, and downloading the Mina zcaps CLI with that command at the bottom, npm install g zcaps CLI, is what you can do to be ready to follow along with that part. So let's get started. The first official slide. Hello, my name is Angus.
And I'm Regina.
So Regina said, my name is Regina, into the,
Yes,
I guess,
that's
the
right.
microphone for the live streamers, right? Because they might not be able to hear you. They should hopefully be able to see you, though. So today is July 15th, or as we say outside the USA, the 15th of July. Welcome. We're going to tell you all about Mina Protocol and Snarkyjs today, and also O1 Labs. Here we go. So follow us on Twitter, please, and give us lots of engagement. You go first, Regina.
Yeah, this is me. I'm Regina. I'm a developer relations engineer at O1 Labs.
This is me, Angus.
Oh, I spelled it wrong. Sorry. Yes.
So usually my name's spelled without a T. My name is Angus Maidment. You can follow me on Twitter at blockchainbeard. I do developer relations, and I tell people all about Mina Protocol and Snarkyjs. And so you should get up and introduce yourself, Florian. Here we go.
I'm here as well. Hello. Hello.
Follow him on Twitter, ZK Trevo. Good stuff.
We have some chairs in the front too. Do you guys want to come up here? You can move. Let me move this here.
Could we? Is that someone's phone? Can we move that? There's another chair here. Let's get the chairs going. There's a chair here, but you can't. Apologies, live streamers. There's some people sorting out some chairs in the audience. So what you can't see is it's so busy, people can't even find anywhere to sit in here. Would you like to do the O1 slide?
Sure. All right. So what's O1 Labs? A lot of people, when I tell them where I work, I usually just say Mina, but O1 Labs is one of the kind of members of the Mina ecosystem. We incubated the Mina Protocol, and now we're working on a bunch of cool tools that makes it easy to write zero-knowledge smart contracts on Mina. But yeah, that's what we are.
Here's the agenda for the workshop today. We're doing the introduction now, and I'm going to be telling you about Mina Protocol and Snarkyjs from a higher level. So I'm going to introduce the concepts to you and tell you how things work. We're going to have kind of a break between these segments. So I'll be doing 15 or 20 minutes of kind of information, basically. I'll be saying a load of things at you. We're going to have some Q&A, so you can ask questions at that point. If you have a question halfway through the presentation, you can stick your hand up and I might take it, or I might just leave them all till the end. Not decided yet. After that kind of Q&A break, we've got, Regina's going to lead the workshop. I'm going to become the computer operator, right? And I'm going to kind of do it in a terminal alongside. So that's why I was saying it's a live interactive demo. So if you've got your laptops out, you can follow along, right? But also, if you're not following along, you'll still be able to see everything happening on the screen, and hopefully you should have a fairly good idea of what's going on. We'll have another Q&A break, / maybe we might have to do some troubleshooting. And then we are going to talk through some of the use cases, kind of features of Snarkyjs in more detail and what you can do with it. It says here 5-minute break, depending on if anyone's still here, you've not all left. We're saving the best till last. We've got Florian, he's going to do a presentation on privacy and scalability using zero knowledge. So that's going to be really good. And we're going to do the closing. So first of all, if you are participating in a hackathon, the place to be is the Mina Protocol Discord server. Usually we have a link, and I think there's a QR code that you can scan, but you can find it if you obviously Google for it, or you can go discord.gg/Mina Protocol. And the channel that you're looking for here, there's a kind of, in the list of channels, there's one called ZK Questions. It's a forum channel, so each question kind of appears as its own little box. And so if you've got technical questions across we weekend for the hackathon, you can ask there, and we've got some people who are really responsive and helpful. I'll also try to be helping people as well if you've got questions. And also you can come and find us around the venue. But the Discord is a really good place to go to ask questions and also search for questions that have already been asked. There's a search bar in there, and it might be that someone's already asked that question. You can get an answer even quicker. There's also a question kind of thread here called Lambda ZK Week, and we've got another channel on the Discord server, which is called Lambda ZK Week, that you can go onto and ask questions and kind of talk amongst people who are here as well. So Discord, we like Discord. If you have questions, go to Discord. ZCAP's questions. Here's some other channels as well, but the main one is ZCAP's questions for Q&A, and ZCAP's general and developers for kind of general discussion. But if you've got questions you need them answered, ZCAP's questions. We've now come to my portion of the slides, an introduction to Mina Protocol and Snarkyjs. As I already said, it's July 15th. My name is Angus. Here's some pictures. These are slides which I usually do kind of on their own, so you've already seen a picture of me, but there's another one of me kind of blending into the sign with a hoodie on. So I live in Edinburgh, in Scotland. That's where I'm from. I do developer relations, and you can follow me on Twitter, again, at blockchainbeard. What I'm going to be talking through today, I'm going to introduce you to the Mina Protocol and zero-knowledge proofs, and I'm going to tell you how ZK work in the Mina ecosystem. I'm going to talk a bit about Snarkyjs, which is the TypeScript library that you can use to build ZK apps, and then zkignite/next steps, which really should have been truncated to just next steps, but it's okay. Before we go through this section, this is a ZK hackathon, so how many people here don't really know anything about ZK, or you're just learning or getting introduced to it? And it's fine, stick your hand up. This is why I'm asking. I'll go through this. I won't speed run it, because there's probably some people here who already know this all already, but sometimes it's good to have a refresher. So a zero-knowledge proof is something, it's a piece of cryptography that you can use to prove information in a private, trustless, and decentralized way. So what does that actually mean? Usually I use the kind of canonical example here of where's Wally. So that's why he's just appeared on screen, to illustrate what you can do with a zero-knowledge proof, kind of how it works. And so the idea is, if you're playing Where's Wally, or if you're from the US, Where's Waldo, there's a big kind of chaotic picture, and this kind of character is hiding somewhere in it, right? And you've got to find where this guy is. He goes on his adventures and gets into lots of situations. So the aim of the game is to find Wally, and if you want to convince someone that you know where he is in the map, then how do you do that, right? You could just point to him on the map and say, there he is, but then you've told that person where Wally is on the map. So now they can go and tell anyone else, I have the answer, right? The thinking of using a zero-knowledge proof to prove something, right, without revealing other information, is you get the Where's Wally map, you get a giant kind of overlay piece of cardboard that you can't see through, you cut an exactly Wally-shaped hole on the cardboard, and then you lay it over the Where's Wally map, right? So then when you show that to someone, you can say, I know where Wally is. Here, you can see, I found him on the map, so you can only see the Wally through the card, not where he is on the map relative to anything else. So what you've proved is, I know where Wally is, because I know where to put the cardboard over, but then that person doesn't see where he is on the map. So you've proven that you know something without revealing the information that they can then go and tell to anyone else. So you can use that for lots of different things. These are a couple of use cases that we usually say to people. Rolling up computation into roll-ups, doing private transactions and things like that, doing voting when you don't necessarily want to reveal your vote. A lot of things to do with identity as well. Digital identity is obviously a big topic, and just verifying computation, like larger bits of computation. So you might be familiar with some other bits of cryptography, and it's useful to think about zero-knowledge proofs in the context of other bits of cryptography, like comparing how they work. So a zero-knowledge proof says that you can basically prove that the output of a program, so that you've run a program, you can verify it efficiently. So you produce a proof and then you can verify it in constant time. So also you don't need to see all of the inputs to the computation, just what are called the constraints. So that gives it privacy, and the constant time verification means that it's efficient. So that has strong use cases for scalability, privacy, and security, as I've already said. So if we compare that to some other cryptographic primitives that you might be familiar with, like a hash function, you can take a piece of data, produce the hash function for it, and then if you sorry, not produce the hash function. You can put the data that you have through a hash function, produce a hash, and then you can give somebody else that hash, and then they can check that they have the same data as you by running the hash function. Okay, so the output of the hash function is the hash, and you verify by running the hash function again. So a zero-knowledge proof is different because you kind of write a computer program, and then you create what's called, in the Mina ecosystem, you create what's called a verification key, right? So you write a computer program, and then you want someone to be able to prove that they've run that. So you give them a prover function, and then you have a verification function as well. So what you do is you take your computer program, you use it to generate this prover function and this verification key, and then you can produce this string called a proof. It's a string, but instead of where you have the hash and you rerun the hash, you don't have to rerun the computation. All you need to do is run this verification function, right, with the verification key that you generated originally, and that is constant time. So you don't have to just rerun all the computation to prove that it happened. And also, there's public key signatures here, which is saying, you know, you can verify that some data was signed by some key by the verification there. It uses the public key of the private key that signed some data. So now we come to Mina Protocol. That was your kind of crash course into kind of zero knowledge and you know, the kind of relevant bits that you need to understand Mina Protocol. So Mina Protocol is a layer 1 blockchain that's built entirely using zero knowledge proofs to do the things that you need to do to run a blockchain. So what makes Mina special is the fact that it uses these zero knowledge proofs, which, as I said earlier, they verify very quickly. So Mina actually has one zero knowledge proof that describes the whole state of the blockchain, right? And you can verify that in constant time. Another thing about the proof system that Mina uses is that the proofs are constant in size as well. So you can actually use, you can create these zero knowledge proofs that summarize the state of the blockchain, and they stay a fixed size, and they're always constant time to verify. So that means that you can do things like run nodes on all sorts of hardware. You can sync nodes very quickly because all you have to do is verify the latest state proof. And there's another drawing here in the middle which kind of shows you some the concept of recursion. So if any of you were at the talk earlier, I was wearing a pickle costume. The recursion layer of the software is called Pickles. And what Pickles allows you to do is recursion of proofs. So you can take proofs and use them to create new proofs. And so then this kind of like, you know, here's a snark, we're putting something into it, and then you put that snark into another snark. So you can keep snarking these up, as we say, but you basically can take proofs, put them into new proofs, and so the whole blockchain actually works. You collapse down all these snarks of lots of different things happening, like transactions, and then it creates this state proof, which is the one proof that verifies the state of the whole chain. So there's also this idea on the right-hand side of interoperability. And so if you have a succinct proof that you can verify quickly, that you can kind of use to verify lots of computation, then, you know, it's plausible that you could take a proof and verify it on another blockchain or computation platform, and then you can verify, you know, everything that's happened on Mina, so you can make interoperable applications. These are kind of things to give shout outs to. One is which research going on to do just that, verify the Mina state in an EVM smart contract. And so then you could conceivably write a ZK app, do a load of computation with Mina, and then take the state proof, verify it in EVM, and then do some EVM smart contract decision making or actions based on that proof. So that's exciting. Also, this is Open Mina, where you can start a Mina node in your web browser, in a browser window. So that's compared to other blockchains where you might need to spin up some hardware and kind of download a massive amount of history to replay to sync your node. With Mina, you just get the latest state proof, verify that, and you're up to date. So yeah, that's pretty cool if you can start your own node in a web browser rather than having to go through some third party or run a big node. So that was kind of a whirlwind introduction to Mina. Now, you're probably wondering, how can I build stuff on this great blockchain network? We're going to talk about ZK apps. You might have heard of a blockchain called Ethereum, and the EVM, the Ethereum virtual machine, the model that they use is on-chain computation. So as a developer, you write a smart contract, and then you deploy it. So the nodes on the Ethereum network all have a copy of your smart contract. Then when a user wants to use your smart contract, they call a method, and then all the nodes on the network run that method from the smart contract that they have a copy of. So you're verifying the computation by having everyone do it and all agreeing on the result, right? So Mina is different. Mina uses off-chain computation with on-chain verification. So the way a ZK app works is, you'll remember earlier I said you take a computer program and you use it to create a prover function and a verification key. So in Mina, when you create that verification key, you send that to the network, okay? So the nodes on the Mina network have a copy of this key, and then the user runs your ZK app. It's all client side, right? All the computation is client side. So they run the ZK app, they run the prover function, and they produce a proof. And then they put a proof in the transaction. The transaction gets sent to the network, and then all the network does is check that proof with the verification key that you uploaded, right? When you deployed the ZK app. So then one of two things happens, right? Your proof is valid against the verification key, therefore state changes and the effects of the smart contract take place. Otherwise, the proof isn't valid and the transaction is rejected. So that gives you a lot of advantages. Number one, there's no gas fees in the same way that you think about them, right? So the cost doesn't scale with the amount of computation that you do. It's a flat fee that's just the transaction fee for sending the proof of what you've done to the network. So now you can do unlimited compute, right, within the bounds of your budget or whatever for compute, physical reality, and then you just send one proof of all the computation you did for one transaction fee. So that's a big difference already. So the cost doesn't scale with how much computation you want to do. Also, it gives your users more privacy because they keep all the computation on their own machine, right? On the client side. You can do lots of different things via recursion as well. So you can generate proofs and bundle them up into other proofs using that concept of recursion. So that gives you a lot of flexibility there to kind of make your own roll-ups essentially to fit your use cases. And also you can do things interoperably if you can verify the proof elsewhere to make decisions somewhere else because again the proofs stay in a fixed size and it verifies in constant time. So this is these diagrams are walking you through what I've just been talking about, which is when you deploy your ZK app, you write your code, you send the verification key to the network, and then when somebody uses your ZK app, you serve the code to them, right, through a web app or whatever, they run the code, which runs the prover function. That produces the proof. They send the proof in a transaction to the network, and then all that happens is the nodes on the network check the proof with the verification key that you gave it, and it's either valid or invalid, right? So ZK apps are composed of methods, and they are the kind of building blocks of ZK apps, right? So each method can take in arguments, and you can kind of you have a very small amount of state storage. So you have some state, you have arguments, and then you can take in data from, it says here, the rest of the world. So when you run the method, the outputs are, you can update the state of the contract, and you can update the state somewhere else. So these are the building blocks of ZK apps. I think I used to have some code in here, but Regina's going to walk you through the code. So now we're just going to skip straight on to Snarkyjs. It's a TypeScript library. So if you have complaints that it's not called Snarkyjs, you can submit a proposal to change the name if you want to, and see if anyone feels strongly the same way. So it's a TypeScript library, but it makes it easy for developers to define, create, and kind of verify zero-knowledge proofs. So there's integration with a lot of tools that you might be familiar with, which make your life easier. It's got good integration with IntelliSense and VS Code. You can use NPM to grab all your bits and pieces, and it's got a Jest for testing. So it's got kind of integration with these tools that you might use already, which make things more convenient. This is some instructions to show you how easy it is to build your first ZK app, which Regina will be talking you through. When you're doing things in Snarkyjs, the first thing that you need to know is that you have to use field elements to store to do data, right? To store your data, to push data around, and that's because of how the cryptography works. It needs to be finite field elements that you use because of how the proof system handles data. So you can store numbers of up to almost 256 bits in a field. So there's a type in Snarkyjs, which is field. And so there's a wee example here, which is saying in table programming, you might use this, where you just say, here's a sum, and it's 1 plus 3. In Snarkyjs, you have to say the sum is a new field, and then you kind of, I've forgotten what the word is, but when you say that there's a new field, you give it an initial value of 1, and then you can use the built-in add method. What's carrying? Currying?
Yeah. Using a function as argument of another function to generate a later argument.
Yes.
That's called currying. Is that what you mean?
I don't think so.
Okay.
Because I've kind of lost confidence because I said something wrong and someone pulled me up on it. So now I have to be careful that I know exactly what I'm saying. Because
we're not going to judge you. A little bit.
Okay, I'll save it for the Q&A and I'll ask you what I mean. But so here, yeah. So you can use the built-in add method on field. You can add another new field to it. So that gives you a field which will be 4, but it's a field type. So yes, if you want to use data in Snarkyjs, it has to be field types. There's also other useful types built in. Here's a list of them. I'm not going to go through them all in the sake of time. This is something that I would usually walk through, but Regina's going to tell you more about it. I just thought I would show off the Mina-themed kind of Mina-colored theme, which you can get off me, I think, somewhere. I can find where it is. Recursion. I talked about recursion and how it powers the blockchain. Now you can use recursion in your apps as well. So this is one of the cool features that really sets Snarkyjs apart, is that it makes recursion accessible to you. So this is an example that we use. It's not a very good card game because everyone has the exact same cards. or maybe that's a really cool game and it's really fun, but we don't know what the rules are for it. So anyway, what you can do with recursion is you can have one player run your code. Say I've played a turn in your game according to the code. They can produce a proof that you can verify that they've taken their turn in a legal way. They can pass that proof to player two. Player two can verify the proof, take their turn, and produce a proof that they've taken their turn in a legal way. But they can include the proof that player one has taken their turn legally in the production of the new proof. So then player three can get the proof and verify that both turns have taken place prior to their turn. So in that way, you can keep going around and chaining it up. And you might notice as well that there's no blockchain here in between. So you can use recursion to basically do off-chain sequential computation like that, and you only have to put it back to the chain if you want to when you feel like it, essentially, or whenever it fits your use case. So people usually come and say, what should I build in the hackathon? Give me some ideas. What I usually say is recursion is a really cool feature that's not a whole lot like what all the other stuff that we've had before. So, that's a good thing to explore to kind of find new and innovative approaches for building apps and solving problems. So, updates and next steps. I think I'm going to, these are a couple of examples basically of projects that people have been building in the ZK Ignite program. So people have been building ZK rollups, kind of layer 2 type things. So that could give you some inspiration if that's something that you were going to think about. Someone's building a keyless wallet. So a wallet that uses Shamir secret sharing to kind of enable a kind of social recovery type thing. So cool approaches to wallets. That's something that's kind of people are working on. It's got an interest from the community. And someone was doing verifying and improving trustworthiness in biotech data. So that was a cool project. There's a whole list of projects that got funded in the program. If you want some insight into the kinds of things that people are building already and the kind of ideas that people are going for, this is a list. You don't have to read it all now. There's a website which I can share with you that you can sign into and see all the funded projects. And there's also a blog post which kind of gives you a quick summary of them as well. I don't know where this QR code goes, but the main points though, the docs and the tutorials are available at docs.minaprotocol.com if you want to dive straight in. The Mina Discord server is there at discord.gg/Mina Protocol. ZKApp's questions channel is where you should go if you have technical questions, or you can search the answers that are already there. That's maybe going to be the fastest way to get an answer to your questions. We have office hours as well on Wednesdays. So I don't know, does this hackathon go on till Wednesday? No. So we won't have office hours, but you have us in person, which is even better. But in future, we have office hours on Wednesdays if you want to come and hang out and ask questions. You can also... DD Discord channel. That was for an old presentation, but you can get me on Twitter as well. And that's really just a kind of surreptitious plug, so you'll follow me. Thanks very much for listening, everyone. If you have any questions and answers, we're going to have a quick Q&A break now. Blank slide.
So I have a question for, since you said, is it working? Okay. Since you said the blockchain was a fixed size.
Yes.
And you were talking about state on chain.
Yes.
What type of state you keep on chain, and what do you use it for, since it's probably not that big, or how big can it be?
When you have a ZK app has 8 fields. So that type that I was talking about earlier, it's just 256 bits. You have 8 of those available to store on-chain state with the ZK app.
And what would you use it for?
Just general
So you can use it for whatever you can think of. I was trying to think of something funny to say about what I would use it for. In the past, I've used it to store an integer that we counted up by clicking a button in the demo app. But on-chain state storage is something. It's one of the kind of complexities that you run into fairly soon with Mina Zcash development, because if you want to keep the state of any data anywhere, you've got to put it on the chain, but you only have 8 fields, which aren't very big. There's been some interesting approaches to it where people have tried bit packing loads of information in and stuff, but the more mainstream way to do it, shall we say, is to represent your data in Merkle trees and essentially collapse the Merkle tree down into the root and put the root of the Merkle tree in the state storage. So then when you change your data, you can log like the changes of the state by recalculating the root and changing that on chain. There's 2 more questions. You can decide whether you pass the microphone left or right.
It's related.
Yeah, you go ahead.
So for example, like a token contract, so you actually would utilize the same model and you would have like 2 Merkle trees in like these 8 fields, one for the accounts and maybe one for the like the balances. And that, I mean, and all of the methods of the token, like a token contract. For example, like if someone wants to build something like an ERC20 token, so essentially like all of the methods will be in a contract.
So what I would say, first of all, is there are custom tokens, and we do have some slides that we're going to tell you about them a little bit more about in the rest of the presentation. Second of all, Regina, how are we on time? I'm not timing at all, by the way, so are we on time?
Yeah, I think we're good.
We're on time-ish. So also, can we pass the microphone to Florian? Because Florian can answer your question more comprehensively.
Yes, hello. So we do have custom tokens on-chain on the layer 1, right? So yeah, we do have custom tokens on the layer 1, which enable you to do transfers and all of that on the layer 1 without requiring a Merkle tree, right? Using a Merkle tree wouldn't be smart in that case because you would have a lot of race conditions and that would highly limit token use, right? So essentially the Mina token is equivalent to a custom token on Mina on the layer 1, right? It's essentially just like an indicator on your transaction that says what token you want to transfer. So they are natively built on-chain and you store that data on-chain as well. Yeah, yeah. So it's essentially, it's not like ERC20, right? It's like native and you do have custom accounts on-chain that have custom tokens associated to them. So.
Thank you, Florian. We've got another question all the way over here, Regina.
Thank you. Just a follow-up question of this burning idea that we have limited space to store information on-chain. My immediate reaction is, okay, but then I still want to store information, and if I'm understanding this correctly, means that now I can store information off-chain, but that information can be verifiable if I keep an index that then I store as a root, as a Merkle root on-chain.
Yes.
Would that make sense?
Yes.
That's the general idea, yeah.
Okay. So then I can effectively have off-chain information that I can just scale as a normal database, as long as I keep in sync an index of that off-chain database with an on-chain Merkle root.
Yes.
That's amazing. Thank you very much.
There's also a couple of ZK Ignite projects that I can share with you that are kind of working on this to try to make it available to developers.
So just wanted to follow up. That is yes, that's how you do it, but that unlocks a very interesting use case about having public and private state, right? So you do have access to public state, obviously, the Merkle root, but you can also locally store private state. That allows you to build like all sorts of private applications where only you have the data, but it's still publicly committed to, and you can publicly interact with people, but you have private data. So that's pretty cool.
Maybe just one big last thing.
Let's say that I effectively have data off-chain that I can read and I can trust because it's verifiably on-chain. The crux of that will be that every time that I mutate my data on a database, that's kind of an attack vector because some malicious actor could maybe manipulate that. Would it be a proper pattern for me to prove that the write operation in that database also happen in a correct way? And then I basically have the chain of custody of that off-chain data secured.
Are you talking about writing a smart contract, like a ZK app, to basically prove all of the
that will prove
modification that
the
happens?
writing operation on a database? So I will like prove that whatever gets written on a database is secure because it was written in a correct way, appropriate way, let's say. Because then I could use that database as a source of truth without being on chain, because it's verifiable.
You can do that in theory. You can use recursive proofs to verify any off-chain computation. You can chain it, and then at some point in the future, which may be now, maybe in a day, you can take all your past computational history, verify it on-chain, and if the proof is valid, you update the new Merkle rule. So yes, in theory, you can do that.
Thank you very much.
Maybe you guys should sit next to each other.
We definitely need to sit next to each other.
Don't worry, I'll be taking over the microphone delivery duties. So I think now, right? So
Okay, yeah,
here we go.
ready.
Now, would you like to speak into this fixed microphone?
Sure.
And I'll kind of...
Leave this here.
Yeah. So I think, do you want to stand here?
Sure.
And then I'll go like this. It's a stretch, right? It's sellotape to the bottom of the table, isn't it? So how about...
It's fine.
That's okay, right?
Yeah.
So I can now... Is this setting up too loud?
Yeah, it's fine.
Sorry.
Can you hear me? Is it good? Okay.
So
Cool.
now what we're going to do is...
Oh. Yeah, that works. Yeah, thanks all for being here. Those questions were like a few levels ahead of what I'm going to talk about here. But yeah, so right now we're at the workshop portion of the talk presentation. So if you have a laptop with you and you want to follow along, it actually is pretty easy to do, but it's also pretty easy to just watch, which is kind of cool too.
So
But yeah.
we said we're probably going to do it there, and then... Here we go.
Okay, cool.
So now everyone should hopefully be able to see both the slides and the terminal. There you go.
You can make it smaller.
What do you want to make smaller?
No, you can.
Is everyone happy with the sizes? Yeah, it's okay.
Okay. There's also one seat at the front if anyone wants to look at it a little bit closer. All right. Okay, let's get started. Can I press down? Okay, cool. So the goal of this workshop is we're going to build a really simple ZK app in like less than 20 minutes. This will give you a chance to see how ZK programs work, but also play around with the tools that we're working on, which is the ZK app CLI and Snarkyjs. So for this portion of the workshop, you don't have to have any experience. It's actually meant to be very like user-friendly for people who are brand new to writing ZK. And what I'll be going over, what we'll be going over today is based off tutorial number 1 in our Mina docs, the Hello World one. So I also recommend that if you are following along, go to this particular link, docs.minaprotocol.com, and kind of search around for tutorial number 1, and that would make it a lot easier to follow along as well. So what are we building today? We're going to build a very super cool app that allows one number to be replaced by its square. Closer. Okay. Okay, this will be blocking my face and my view. All right, so yeah, for example, if we provide a number, let's set a number to 3, this number can only be replaced by its square, 9. That's just kind of the rule of this particular simple app. And so building a ZK app is super, super easy. There's kind of broken down, kind of similar to what Angus did earlier with the 5 steps. We're going to install the CLI. That's step number 1. Then we're going to create a new project, write the smart contract over there, and then we'll interact with a local blockchain and then deploy it to testnet. And we can do this all today. You get to watch it happen. I think you mentioned this earlier, but the CLI is basically one of the tools that makes it super easy to write ZK smart contracts. It has project scaffolding. Oh, all of you were here, but this is basically what Angus said. And also includes, most importantly, Snarkyjs, which is the library that we'll be using to write our smart contracts. So to install the CLI, all you need to do is go to your terminal, enter an npm install ZK app CLI. And this will make a ZK command available on your system, and that's what we're going to be using today. It's loading. And what's going to happen is, also, if you do have the CLI, it's been updated recently to 11.0, so I recommend also checking to see what version you are. And sometimes if you run into bugs or issues, check the version. Oh yeah, you're up to date. Nice. I don't think so. That's a really good idea, though. I'll add it. You'll get credit for that. To update it, you just enter that last command again, npm, and then there should be a better way.
Yeah, either run npm install again, or you might need to do npm update.
Cool. And so this is what the CLI offers. You can see you have a bunch of ZK commands. You have ZK project, ZK file, example, system. And this will be pretty useful for when you're building your own ZK app. So you're done already with step number 1, download the CLI. And now we're going to start creating a new project. So to create a new project, all you need to do is enter in ZK project and the name of your project. For our project name, we'll call it 01-hello world. But it can be anything you want. And it'll create, do you want to maybe finish? It'll give you an option to pick a UI. You can do none, yeah. That part is outside the scope of today's workshop, but just to let you know, you can build a UI with your ZK. It has all the, what would you call it? It has a setup for you to, yes. Yes.
It'll set up the bits and pieces for various different UI frameworks.
Okay, so it's creating setting up a project. It's moving, I think, hopefully. And so this is when it's done installing and setting up a new project, this is kind of what the project structure will look like. Maybe we'll wait a little bit. Okay. So if you go into your project, your new Hello World project, you'll see a bunch of folders and files. The two that we're focusing on today is a source file and build file. The source file is what's going to contain our TypeScript smart contract, and build is where the JavaScript code will be after the TypeScript code is compiled. Okay. So we need to prepare the project because when we typed in ZK project, it had some default files built in. It had an add smart contract, and an interact file. Let's get rid of that for today. We're going to create a brand new file called Square. Yeah, so ZK file is another one of the commands that comes with the CLI. They'll be pretty helpful for you when it comes to writing your smart contract. And you'll see right there, it says it created 2 new files, Square and a Square test file.
Should we remove that and test?
Yes, it should be removed. Right, it is removed here.
Yeah, I removed them.
Cool.
And you can too.
Yeah, you can get rid of it. You don't need it. Or you can rename it. They just come with your folder. Okay. So if you take a look at your source directory, you should have square, a square test file, an index file, and your main TypeScript file. And we'll go through them a little bit later. So we are done with step 2, creating a brand new project. And now we get to go into the fun part, which is writing the smart contract. So the best text editor to use for writing a ZK app, we recommend VS Code. Ooh, what you making? You just exit, close out.
How do you add like a new workspace or something?
You can just type code and dot in your terminal.
What, in the inbuilt terminal?
No, in the, yeah.
Just type code and then dot.
Code dot.
I think you need to install something first. Or just open up the file.
Where were we? Is it home?
You can go back to the terminal and type in open dot.
This was in.
Yeah, if you go there in CD or Goose. What happens if you click open dot or open the folder and then you open with VS Code?
What, in Finder?
Yeah.
I don't know how to get to home though.
Can you go into there and type in open dot?
Or Finder.
Yeah. Or open and then dot. Let's see. Okay, and then
okay.
open this with VS Code. Yeah. You can go. You can select all of it and then.
Who was like, oh,
Edit, or you can select all. There. And then you open with other VS Code. Oh, you can search. Yeah, it should be under application. Scroll. Yeah, there it is.
Right.
You need to start code. Okay, back to where we were. VS Code is open, and we are going to write a smart contract. But you can exit all of that.
I'll do that while I'll get
Okay.
the, where's it? Square?
I think it's further. Oh, wait. It's under your source file. In there.
Did it open the?
Yeah.
Just open this.
There it is.
Here we go. Sorry about that, everyone. So,
Okay.
do we need to go back to?
Yeah, let's go back to the slides. Yeah, it's okay. We can move forward from there. And then thanks. Okay. Just a quick overview of what the smart contract looks like. There's two main parts. There's an import statement
Should we
here.
maybe full screen this?
Sure.
There you go.
Yeah, there's an import statement at the top, and this is what we're importing from the Snarkyjs library. And our actual smart contract, what we're writing is at the bottom using the smart contract class. And yeah, so one of the distinct features of any ZK app that you're working with, you'll have like an import statement with what you need, from Snarkyjs. And you can see we'll skip this, the full library on Mina docs. And for example, in this smart contract, the methods we're using is mul, get, and set, which we'll talk about a little bit later. Okay. Maybe we'll go over this a little bit, but here's an example. I think earlier Angus mentioned that the native number type in Snarkyjs is field. So most of the time you'll see that you have to import field. If you want to write a smart contract, you need to make sure that you have the smart contract class imported. Let's see. I think the only thing that's, yeah, you can look up method and state yourself, but basically if you're working with methods, you usually have a method decorator. And if you're working with any state that's stored on chain that we talked about a little bit earlier, you'll have like an @state decorator as well.
So also, maybe worth mentioning at this point, here's how I like to do it, is by copying it off GitHub. So if you don't want to type all this stuff out, the code is available somewhere.
Yes.
Is it in the docs2 repo?
Yes.
Let's go there.
Oh yeah, you can go there.
So, is it in zcamps?
Yes. We have
Is it
tutorials. Yeah.
Is it in Hello World, or is it?
That one. Yeah.
This is the markdown. So
Oh.
I was thinking, is the actual code somewhere?
It's embedded.
Oh. Thank you. Thank you.
Okay, maybe we just go to the docs then. Okay.
Yeah.
So use the tutorial.
Mm-hmm.
Use
The
the
top.
go through.
Mhm.
And then have we put in index TS yet?
No, not yet.
Oh, I remember you need to use this button as well. So I'll go back to the slides.
Okay. Maybe we can copy this a little bit later. But okay. So let's go back to our smart contract. We are creating a smart contract called Square. And you know it's a smart contract because it's extending from the smart contract class. And we're going to have in our particular smart contract, we'll have a one element on-chain state called num, and we'll set it to a field element. Yeah, every smart contract class you have to initiate it. There's an initiation function here, and we're also setting the value of num to 3 in this particular line. And this is kind of the logic behind our app. And here we're basically saying that, you know, we'll have the current state will be set to the num, and the only way for us to update the current state is if we replace it with a square. You can kind of read this a little bit or copy this over and read it in your own time, but just wanted to give you a sense of how clean it looks. And yeah, it seems pretty readable. Yeah, any questions?
Why did you choose decorators?
That is a good question.
Why do we use decorator? Do we know? Florian?
That's the current class API, right? And the decorator is indicating. So that's the current class API. We have a slightly different API for recursive proofs. It's called ZK program, but the decorator is indicating whether or not you want to generate a proof of the method, right? So if you add the decorator and then you execute the update method, you will generate a proof. Right? But we do have a slightly different API for the recursive proofs, which is not a class, but more like a object that allows you to specify entries in the object and then generate proofs of the methods that you define. So
decorators indicate what I want to make a proof of.
yeah.
Thank you, Florian.
Cool. Good question. I learned something. So one thing that's interesting to know is, you know, we have a bunch of methods that, like, you know, with writing ZK, it's a lot of proofs are being generated. And what's really going on behind the scenes is when we are creating a method, these methods are called assertions. And what's happening here is whenever we're creating a method, it's actually generating a proof. That makes sense, right? But yeah, but just like, it's basically, this is kind of how the magic of Snarkyjs works.
So
Yeah.
can I ask a question?
Yeah.
So for example, in this example, let's say that what you want to show others is that the computation is right. So you would share with someone like the code, for example,
Yeah.
they would be able to produce like the same verification key if they want to, but the input is a private thing, right?
Yes, the input would be private, but we are, is there a question, what are you asking, like if the whole part is
Like
question?
anyone without obviously the inputs would be able to
So everyone that you want to let interact with that contract, you have to send the contract code over. Then you can compile the contract, which gives you a unique verification key, which belongs to exactly that piece of code. Then you store that code on-chain, and then the user can generate the proof by passing in a square, which is private. So whatever they pass in as method arguments is private input. They generate a proof, and then they send the proof with instructions to the chain. It verifies with the given account, with the given verification key, and then updates the state.
Right. I think my question is, if I deploy the contract myself and I pass the code, like, is there an easy way for someone to see that it maps one-to-one, like the verification?
Yeah. So if you compile the contract, like if you give me your contract, I have to compile it in order to prove it. And then I can just check that the verification key matches with the smart contract that I want to interact with. So the verification key is deterministic, and it's always the same, right? So
it's part of the attestation that the client is going to do.
yeah, you can just think about the verification key like a hash of the contract code, essentially. So it's unique and only belongs to that contract. So that's, yeah.
Thank you.
And so as a result of that as well, if someone gives you code that they want you to run for some nefarious purpose and it's different to the smart contract code, right? If you run it, you can run the code, but the proof that you produce won't match the verification key. So that's usually what people are asking is, what happens if somebody changes the code because they're just serving it from a web server? Well, then the proof won't match the verification key. The proof that you produce only matches the verification key if it's the exact same code. The verification key is stored on the network when you deploy your ZK app.
And is that part of the size of the blockchain, or does it contain verification key for every program? Will that keep on increasing, right?
For every ZK app, yeah.
Every ZK app stores a verification key.
Yes.
But your question is like, does the blockchain get bigger, right? Or,
It increases the size of
Okay.
the carbon state.
Probably the meta question is, so this code, that's part of, where is this code stored? Because the blockchain size is small. So where is this code actually stored, like on chain?
It's stored on chain, yes.
Does this will add to the size of the blockchain?
Are you talking about the code?
like this smart contract?
The smart contract
Yeah.
code isn't stored on chain. So you got to serve it to someone, to users somehow.
Usually be off chain. All you're sending,
And the verification key will be on chain.
The verification key
Correct.
is on chain, but the verification key is only a constant size. So if every single app has a verification key, it doesn't matter how big the app itself is, but the verification key is only constant size.
But if there are thousands of programs, then the verification key will increase, right? So that will also
But
increase the size.
there's more verification keys, so yes, it does increase the state of the current, it increases the size of the current state. But Mina doesn't store the history, so it only stores in one current state, so it's okay. Especially since everything is constant size, it's like sustainable.
cool. Yeah, feel free to ask more questions. We want this to be as useful to everyone as possible. But this kind of maybe answers your question a little bit. So normally what happens is you write your smart contract, what we wrote there, and you also want to build a UI. And so your UI smart contract will be hosted somewhere outside the blockchain network. And this is just an essential part of usually how people will interact with a ZK app. In our case, we aren't doing the UI. We are just writing a script that will kind of like represent a UI and interact with our smart contract. But if you want to know more about how to write a UI, there is a link here that you can follow and learn a little bit more. Okay, so the next step after this is normally we would prepare a smart contract in our index file. So by writing import square from this particular file, you're saying that we are going to interact with this particular smart contract. Also, right here, this index file is kind of the entry point for your project and where your UI will interact with your smart contract. So quick recap, we wrote a smart contract called Square, and then we update our index file that can be accessible from a UI or a script. And our next step now is to test it out on a local blockchain. So that's step 4. Yeah, so local blockchain is super useful in developing a ZK app. It could help you test things really quickly. But you can also play around with, we do have a live test net called Berkeley, and you can also, deploy and build around with that to get faster feedback. So this is the script I mentioned. Instead of a UI, we're just building a quick script called main. And I'm not going to go into too many detail about what's going on here, but just, I guess the key parts to keep in mind is, you have your import statement, as I mentioned earlier. Whenever working in Snarkyjs, you'll see import blah, blah, blah from Snarkyjs in every single file. We'll be setting up a local blockchain, and then there's a few, I guess we're going to test it out. We're going to deploy our smart contract with Square, but we also will interact with the smart contract to test it out, like see if it's actually working as expected. So the import statement, this is us setting up a local blockchain. And this is us deploying our ZK app to a Mina address. And so, yeah, for example, let's say we initially set our num variable to 3, and we'll write a console log statement testing to see if it is 3. And it should be, because originally we set this particular variable to 3. We'll also test this out by trying out a few numbers. We'll see if we can update our on-chain state to 9. It should work, because 9 is square 3. And then after that, we can also check to see if we'll check a fail statement and see, can we update it to 75, and it should fail. Yeah, so if you run your script, you can see this is kind of what it looks like. Yeah, we tested in the beginning to see if our state was 3, it was, and we tried out to see if it can update to 9, it worked, and then, yeah, it's more magical if you do it yourself, but this is kind of how it should look. But yeah, so at this point, you're ready to deploy to a live network, to Berkeley, and that's actually pretty simple. Berkeley is Mina's live public testnet, and right now we're kind of at the final stage of testing everything out and having ZK apps be available on our mainnet soon. And so thanks to the CLI, you can actually deploy your smart contract pretty easily. First, you just enter in ZK config. And right after that, they'll give you the option to select which network you want to be using. In our case, it's Berkeley. And you would just enter this in very, very slowly. And if you would like to request some funds for the testnet, this is a link here. And this usually takes a few minutes. So even if we did this completely live, we stayed to wait a little bit. And yeah, once you have your funds, you could deploy to Berkeley, and your smart contract is on a live network. Yeah, so this is kind of, how long did that take? 20 minutes. But we had a little technical difficulties. But yeah, that is all the steps it takes to build a ZK app and deploy it. It's not too bad, especially if you have the repo right next to you. Does anyone have any questions about this so far? No? Okay. Thank you for the clap. Yeah.
So since Mina only keeps the current state of the blockchain, or like the current state of the chain, where do you query the older proofs or the verification key? Where do they live? Do they like?
Helena.
So the verification keys are stored on-chain. They're a part of the current state. So the verification key, the 8 fields where you're storing your Merkle roots, those are on-chain, and the account balances are also a part of the current state. So all those things are a part of the current state. So you're not, the normal Mina nodes are not storing the past states. So because Mina is not relying on the past state for its security. So for a normal node that's participating in consensus, it just throws away the past states, and it's only keeping a track of the current state, right? So for literally every other blockchain, right, like Ethereum, they're keeping track of every single block going back to Genesis. And so even with Ethereum, it's like the current state is huge. And not only are you storing the current state, but you're also storing all the diffs going back to the Genesis block. That's a lot of data, right? Because not only are you storing like
like the current, but also all the past. But with Mina, you're only storing the current state, and you're not really storing that much because the verification key, that's only going, all the verification keys in Mina are the same size because all they have to do is verify a proof, and all the proofs are proofs of different things, but they're all going to be the same size, and they're all going to take the same amount of time to verify. So the verification keys are all the same size. You only have 8 fields of data. That's a constant amount of data, also not that much. And then the account balance, that's also not that much data. So the current state is just, it's just not that big. Yeah, so.
But it will not accumulate more when you store, keep on storing, eventually it will grow, right?
If more people if more people join Mina and more people open accounts on the blockchain, and if more people add more ZK apps, yes, then the current state does absolutely grow. But I don't, it hasn't been like a huge problem, and we don't anticipate it. I mean, if you think that's a problem, imagine what Ethereum is dealing with. They're not just storing, you know, this limited amount of data, they're storing all the ZK app, the entire on-chain like smart contract is on there, all the data is on there. So right, so whatever problems that we're dealing with, like Ethereum is dealing with so much more of that same problem.
Could you introduce yourself quickly?
I am Helena. I am an engineer at O1 Labs. Today, the emotional support engineer of the presentation. Yes.
I didn't want you to think I just handed just given up and handed the microphone to an audience member.
Yeah.
Mind you, we do have amazing community members who can answer questions certainly much better than me most of the time. So
Yeah.
Also, I would just like to say on that point as well, I think people ask this kind of question, right, where it's like, so there's a small state proof, you know, and you may have seen the kind of messaging that's like, you know, the blockchain is 22 kilobytes, right? But then there's also this talk of storing the data on chain. So, you know, there's kind of a big diagram of all the different kinds of nodes that run on the network. But the point is that some of this data gets stored by node operators who participate in running the network and the consensus. But if you want to spin up your own node, you only need the state proof, right? And then there's the Merkle path. I was about to say root, because I think of it as like a root through the tree, but it's not. It's the root at the end of the tree. But it's the Merkle path. So you need the Merkle path to your account to get the state of your account, and then the state proof, which is very small. So when you hear about the light blockchain, it means that you only need that much data to start up a node and verify the state of your account to interact with the blockchain. There's other nodes that store this other data. It is somewhere, so you can access it. I hope that made sense. Also, there was another question here.
Yeah, thank you. Related to the architecture and the blockchain itself, my question is, I understand that you don't have like gas wars because like people are not also deploying contracts themselves, but do you have some sort of prevention of, I mean, a mechanism to prevent a lot of like spam? And is there a scenario in which like the fees would increase? And maybe if it's not, if it's okay, like are validators getting paid?
I will field this one briefly by saying there is conceivably, so the transaction fees are for block space, like in other blockchains. So if everyone wants to use it at the same time, it's conceivable that the fees go up because people will start sending in transaction with higher fees. And so do either of you want to add more detail about the validators? Who do I choose? I'll go you first, Lena.
Whenever you interact with the validator, you pay a constant fee, or you pay the fee. So if you only need to interact with the validator like once in your lifetime, then you just pay that one fee. Practically speaking, you probably will be interacting with the validator. You know, if, for example, in the example that he gave is like, if you have like a living database and you're trying constantly to be like, making sure that this database has is like Merkle rooted, is like hashed up Merkle rooted, and you're constantly updating that Merkle root, then every time you update that Merkle root, you're going to interact with the validator, and that's going to cost you whatever the fee is. As for whether the fee is going to be stable, I personally don't know. I would imagine so because like no matter how complicated the original transaction, and no matter how complicated it is to accomplish the original computation, that computation is happening off chain, so you just have to pay the fee in order to update the Merkle root. I don't think that's like that much computation, and I don't think it's going to be like that high demand, but I don't have a crystal ball. I don't know if like there's going to be like huge turbulence there, so I hope that answers the question.
Yep, so just briefly adding, when it comes to account storage, there is a small account creation fee, a one-time setup, so you can't spam everything and just create accounts that take up space. And when it comes to sort of like spamming transactions, it's actually not easy to spam transactions because you need to invest computation in order to generate proofs, right? I mean, you can do that, but then you will have to pay in computation, which may cost cloud instance and stuff like that. So, and plus everything what has been said. So.
Kind of two small questions. One small question, one big question, actually. What's the current roadmap to get this on mainnet?
That's a good question.
Tricky one, I know.
Yeah.
So let's transfer the microphone.
Yes, so two things. There's a public roadmap on the Mina Protocol website indicating all sorts of stuff. There have recently been two MIPs, Mina Improvement Proposals. I think they have been sort of like voted for, approved by the community, which included the proof system, Kimchi, as well as the CK app execution verification layer protocol. I believe there's an incentivized network program that people could sign up recently. Other than that, talk to Mina Foundation people.
Hello, Mina Foundation people. I would love to accelerate that. Follow-up question. You didn't mention in this great demo nullifiers. So I wonder if it's too much out of scope of what you want to show today, or if you can mention it as an intuition of how we can use nullifiers here.
I think mainly because we don't have any slides about it, it's probably out of scope to establish intuition. However, Florian might be able to...
If we get to it, I will be talking about it. Clear. Thank you.
There you go. And so now, because of that request as well, I feel like it's a good time to segue into Florian's slides. Oh, we've got the use cases as well. I feel like we're probably going to skip the use cases and go straight to Florian. And if you want to mention...
We could do this at the end.
We can do this at the end if
Yeah.
anyone's interested. But if you want to mention some things about nullifiers as well, that's probably a good way to do it. So let's just... Where do Florian's slides start?
Further down, furthermore. Yeah, all the way down. Past that. Yeah, like 170 slides. No, further up, further up. Yeah.
Like 140 maybe, so somewhere around there.
Huzzah!
Yeah. One more higher.
Slides.
Yeah, one more.
Whoa,
Okay.
Yeah, this
I'm
one.
going the wrong way. Okay.
Yeah.
Slideshow?
Okay.
Perfect.
Do you,
Florian.
wait, do you want the speaker notes on the screen?
No,
Okay.
I don't have notes. I never take notes. So, yeah, we spoke about, I guess, the sort of like basics of Snarkyjs and Mina. And now I will hurry up, but I want to, I guess, introduce a more complex use case and sort of like talk about the architecture. This is something that we have been looking into for a while. We also wrote a blog post about that, Phil over there and me including. So I will be briefly talking about that. And it is, as you could just tell by the title, private voting. And yeah, just maybe take a step back and consider what we want to do with private voting, what private voting is about, and what sort of like the main points are that we want to fix. Starting obviously with privacy, right? A voting application is supposed to be private. We don't want to leak any information. It should be scalable. We don't want users to pay a lot of fee, secure, and it should also be hiding. So what does that mean? Privacy is, I guess, the most obvious use case. It means that a user should be able to prove their identity without leaking or revealing their identity, address, like voting weight, their on-chain account data, whatever. So we want to like keep that private. Additionally, the second point, no one should be able to track back votes to individual voters, right? So if I cast a vote on the blockchain, for example, it shouldn't be able to be traceable back to a certain user's identity, be it their exact identity or maybe even by the voting weight, right? We don't want to differentiate between voters that only have 1 Ethereum and voters that have a massive stake, essentially. Then it should be scalable and efficient. Scalable meaning that users shouldn't have to pay for a vote necessarily. I guess there are sort of like engineering or like social problems involved. If you have to pay for a vote, you might not want to do that, right? If you have to pay for it. So we want to make it free as best as we can. And additionally, it should be scalable, right? Should be scalable for many people. So that's another important thing. And security, of course, that's a big one. The outcome of the election should be tamper-proof. We don't want anyone to be able to impact that result negatively. And additionally, voters should only be able to vote once. In most voting applications, I guess, you can also look at sort of like proposals and all sort of stuff where you have multiple choice. But ideally, we only want to vote once. And the last sort of like important property that I also talked about just a second ago is that we want to hide the movement and the content of votes from the public, right? So we don't want to necessarily see, is it a yes, is it a no, where is it moving, where is it coming from? That has multiple reasons, again, sort of like privacy from earlier, as well as social manipulation, I guess. If you see your favorite whale with a lot of stake voting for a very specific thing, it does impact you to some extent, so you want to prevent that. And yeah, how do we do that? How do we start? It's just going to be a very high overview, introducing you to a potential architecture, potential solutions. But in order to sort of like keep the state private and improve privacy of voter identity, we can simply use Merkle trees. I think most of you should know what Merkle trees are, but they allow you to prove inclusion in a set. So we would have to specify a set of voters, depending on maybe their voting weight, if they hold an NFT, some other identity-based, I guess, requirement. And then the user can simply, within a zero-knowledge proof, of course, prove that they are a part of that certain Merkle tree without revealing which entry they are, who they are. So yeah. For scalability and efficiency, we, of course, because we are sort of like Mina, we want to use off-chain execution and only verify the result on-chain. And because we want to do it off-chain as well, we want to use recursive proofs for parallel processing and scaling, and additionally, ideally, no fees. We can achieve that by unlimited off-chain execution. We could use it, for example, a vote sequencer that is taking all those proofs in and then recursively verifying them. That would mean, in theory, there are no fees for users because no one wants to pay for vote. So, security is also a very important one. Of course, we don't want anyone to tamper with the result. For that, we use zero-knowledge proofs, of course, for computational integrity. And we simply do that by sort of like proving on the user side that they are who they claim they are. And we also prove the tally of the votes. And we will use nullifiers to, for example, prevent double voting, because we also don't want to allow an entity to vote just multiple times for their favorite candidate, because that wouldn't be, I guess, democracy. So yeah, and the last aspect is hiding. Essentially, we want to hide the flow of transactions from the public. We want to hide the contents of the votes. And yeah, but we still want to allow that the votes should be able to be counted, tallied, without having to decrypt them. And how do we do that? Very fancy technology called homomorphic encryption.
and we will be using that for sort of like tallying the votes and encrypting them. So just gonna talk a bit about a couple of these primitives that I just mentioned. Nullifiers, now we're gonna talk about them. Just very simply said, they are just a cryptographic primitive that allow someone to like anonymously keep track of actions. And in a more fancier speech, nullifiers are a public commitment to a specific account, and they allow you to forbid actions like double spending, and they essentially prove consistent identity between unrelated actions. So we implemented that in Snarkyjs, so it's available as a first-class primitive. And the idea is that a user would generate a nullifier inside their secure enclave. Secure enclave meaning a browser wallet, your ledger, whatever. And they would then simply verify the nullifier within a CK proof in their browser on their computer without leaking sort of like any private data. And because we previously talked about the Mina, sort of like storage requirements, we can also store nullifiers in Merkle trees, commit to them publicly, but still the private user identity is never being leaked. So how do we do that? We have implemented the nullifier scheme that Ayush Gupta and Kobi Gherkin sort of like developed. There's a paper link here. It's the Plum nullifier scheme. I think it was introduced last or previous CK Summit in Berlin last year. So there's the paper here. You can take a look. There's the example right there. It's available in Snarkyjs as well. So if you want to use first-class nullifiers in Snarkyjs, just go ahead, do that. Again, the very important thing there is that it doesn't leak any private keys, right? That's a very important thing. You generate the nullifier in your wallet, where it's secure. You don't have to take the private key and put it into a proof. Like essentially, no one would want to take their private key and use it as an input into a website that you don't know what it's doing. So that's a very important part. And yeah, again, available sort of like as a first-class citizen in Snarkyjs, as a first-class primitive, ready to be used and ready for you to build exciting applications with that. It could be voting, that could be private actions, private transfers, mixers, whatever, all sorts of very interesting things. The second one that I mentioned is homomorphic encryption. Unfortunately, not fully homomorphic encryption. That may be a bit too expensive in a Snark. But still, we want to take a look at that. It allows you to do sort of like operations on encrypted data. So what you would do is you have a yes vote or no vote. You would encrypt that, send that off. No one would be able to see that vote. But you can still take all votes, 5 votes, and count them together, have sort of like a state of the final vote without needing to know the exact information about the vote, right? So they should be encrypted. The user encrypts the votes locally and then sends them off, but you can still tally them. So I actually implemented a small partial homomorphic encryption library after the Al-Gamal scheme, which is available there. You can just import it as a, I guess, library and use it as well. It supports multiplications over finite fields. And in theory, with a little, I guess, disclaimer, it's additive over group points. But yeah, still, if you want to do it, you can take a look, use it in your application. I guess that's a bit of a self-promotion. I hope that's not too far. But yeah, so you can do it. Simply encrypt field elements. You're going to encrypt a 5 with your private key that you generate. A public key, actually, then you can just multiply both encrypted data pieces into a new variable, and then you can decrypt it using the private key, and then just for a sanity check, that you're just going to multiply the plain field elements. 5 times 5 is 25, and because that assertion will fail if that's not the case, you essentially multiply 2 elements which were encrypted without having to decrypt them first. So that's a cool little, I guess, technology. And again, up there's the partial thing in brackets. It's only partial. It's only allowing you to do multiplication or addition, depending on if you're operating on fields or group elements. There are much more sort of like sophisticated schemes that are full homomorphic encryption, but they are quite expensive to do, and yeah. So now we can just take a step back, or maybe go a step ahead and pull everything that we just talked about together and construct our, I guess, end-to-end off-chain voting application. We would start with the user. So essentially, the user would generate a proof locally in their browser of their identity and their choice of vote. So a yes, a no, a maybe, whatever you offer. The vote will then be sent to a sequencer instead of directly verifying it on-chain, because we will do that step later. That, again, has the bonus that we can scale it, as well as the user doesn't have to pay any annoying fees to vote. The sequencer would then go ahead and collect all votes and verify them as a first step, making sure that they are indeed correct. After enough votes have been collected, the sequencer will start aggregating them, so sort of like counting them together, tallying, using homomorphic encryption again, without having to decrypt them. And if they don't decrypt them, they also don't get to see the contents of the vote, so they don't see the intermediate result, and they couldn't do anything fancy with it. So, and at the end of the tallying process, the final result and the final proof of the result, which is essentially just the recursive proof of all previous proofs, will be sent to the smart contract for verification by the sequencer. And that allows you to sort of like combine hundreds, thousands, tens of thousands of proofs into only one proof that you verify only once, instead of doing it 100,000 times individually. So yeah, the smart contract would then verify the final proof and update the on-chain state with the result. And additionally, at some point, the smart contract would also decrypt the final result, which is still encrypted using the homomorphic encryption scheme that I talked about earlier, and then sort of like update the on-chain state with the plain result, and then sort of like invoking some actions about whoever won. That's I guess a diagram that I just put into. I talked about this, or we talked about this in the CK Ignite 1 cohort a couple of months ago. There's even a YouTube recording about it, going much more into detail, but this is just sort of overall the flow. You have Mina over here, the on-chain state, then you have the nullifier tree up there, the sequencers, and also the recursion program going a bit more into detail. If you are interested in learning more about this particular diagram, I would recommend you to go ahead and look at the, I think it's either O1 Labs or Mina Foundation, a Mina Protocol YouTube channel. There is I think a 90-minute workshop going into detail, building this from the very scratch to the very end. And there's also some source code at the end. But it's important to mention it's certainly not perfect, just a quick proof of concept. And yeah, so there are some open questions, for example, backwards traceability of encrypted votes. If the private key, if the private key of the homomorphic encryption scheme gets leaked, you can, in theory, trace back each individual vote and decrypt them. So there's one. Relaying votes over the network is still one thing that I didn't consider at all. For example, if a user sends something to a sequencer, you could still see the IP, wouldn't be as private. And there may even be some incentives that you have to introduce, for example, sequencers. But yeah, we are just focused on the, I guess, poor Snarkyjs implementation of it, of the poor CK app architecture sort of like point of view, without going into too much detail, but just sort of like give you an overview, just some ideas that you may be interested in. And yeah, I think I'm just gonna do that.
Yeah.
Yeah. Yeah.
Maybe questions, and then
Yeah.
later we can go into use cases.
So yeah, do you have any questions about the very particular voting example? Yes. Do we have the microphone delivery guy?
You jump type in.
Hello? Yeah, so you mentioned being able to doing it in parallel.
Yeah.
Is that the sequencer collecting these and
Yeah.
then doing them recursively?
Yeah, so we sort of like, I guess we have two kinds of recursion. One recursion being you have a proof, you verify that proof within another proof, and sort of like a linear recursion. But you can also verify two proofs at once. So you can just think about a Merkle tree. Merkle tree is very cool. like a binary tree, whatever. And each of these things is a proof, right? And then what you would do is essentially spin up cloud instances or like workers in parallel. And each of the worker would in parallel take 2 proofs and spit out another one. And then you can, in theory, shut down one of these workers. And then the last worker would take the previous 2 proofs and aggregate them, verify them. And you would end up with sort of like one main proof that verifies all the previous sort of like leaves of the tree. You can parallelize that quite nicely. There's also a library in my GitHub repository somewhere. I don't know if I linked it, but yeah. So that's what I meant by sort of like scaling that. Yeah.
In the very last step where you decrypt the information, are you also decrypting who casted the vote?
No. So
how do you lose that information?
Sorry?
How do you lose that information? How you get rid of that information?
Yeah.
Not
So
to be encrypted?
the vote essentially is a piece of data saying yes, no, maybe, whatever you want to vote for, and then a proof, and of a CK proof, right? And the zero knowledge proof proves that you are a member of a Merkle tree, of a list of eligible voters, but you never leak that data, right? You're not, when you decrypt the sort of like vote, the only thing that you're decrypting is the result of the vote itself, but you never decrypt the CK proof, right? The CK proof always says it is a eligible voter, and then there is some vote associated with that proof, yes or no, and that sort of like vote data is encrypted and then decrypted, but you never lose the privacy. It's only like you will be able to see someone voted yes, and you may even be able to see if there's like vote bait engaged, and include you will even be seeing that someone with a lot of Ethereum voted yes, right? That is the thing, right? But you will never be able to decrypt the exact on-chain identity or something like that, right? It's sort of like the metadata essentially that you have to encrypt.
Clear, thank you.
Yeah.
Any other questions?
I think it was probably a lot to take in, so want to go in?
Yeah, how's everyone feeling? Because we have one more portion of this workshop, but it's mainly for maybe people who still want to learn more about Snarkyjs. It's going through like common use cases. If you'd like to stick around, and I can talk about that, but also I don't know. I've noticed different levels or progress for different groups, but we can also just take like a couple minute break, and if you guys want to head out now. But if you want to stick around and listen to the use case portion of the talk, let me know. Yeah. Let's go now. Okay. All right. Is everyone okay?
You can all leave now if you would like to.
Yeah. Yes,
Do you
please
mean
do.
let's
Yes.
go-
I know you guys are all packed up, but yes.
Do you mean let's go now as in let's leave now? Or you want to do the slides
Okay.
now?
Okay. Sounds good.
We're going to wait a couple of minutes for people to come back.
Yeah.
Okay. You're leaving for good this time. Well, you're welcome. Thank you for coming.
Oh yeah, this is it. Have any of you guys worked with Snarkyjs before? I'm curious to know what everyone's experience is. Oh, you did not? Oh, okay, exciting, cool. Yeah. Nice. Yeah, this is good time to practice. Have you guys worked with Snarkyjs before, or like? I did the hackathon with Developer Now. Oh no way! You were part of that. The Developer Now. Okay, cool.
Welcome.
Me too.
Welcome. Did you Sorry? Did you reply to my message in the chat, the Telegram chat today? Are you rude today? No. No. What's your name? Ruth. Yeah, your name with this place. R-U-T-E. Yeah. That is F. Yeah. F-I-G. How do I say it? I said, are you Ruth today? You're like, no. Yeah, you can say Ruth. Just Ruth? Yeah. Okay. So. This is off the record, so. Wait, are we finished the stream now? Are we off the stream?
We're still on streaming. Okay.
No.
Thanks, Yasser. So I was going to say, I sent a message in one of the many Telegram